We are in section 11.3, the integral test and estimates as sums. In general, it is difficult to find the exact sum of a series. In the next few sections, we will learn several tests that enable us to determine whether a series converges or diverges without explicitly finding its sum. In some cases, we can find a good estimate of the sum. And so that's what the next few sections will be doing. And so this one at the top of page 10 is the integral test. So the integral test states that suppose that if f is continuous, positive, and a decreasing function, so you need to make sure that you show all three of these in order to use the integral test. Showing that a function's decreasing, you can use the first derivative test. And remember, the first derivative test was used to find local extrema, and so you can show that it is decreasing over that interval from 1 to infinity. And let a sub n equal f of n. Then suppose that the series from n equals 1 to infinity of a sub n is convergent. So it's convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. In other words, so we have two things right here to start. If the integral from 1 to infinity of f of x dx is convergent, then the sum from n equals 1 to infinity of a sub n is also convergent. Whereas if the integral from 1 to infinity of f of x dx is divergent, then the sum is also going to be divergent. And if you remember when we dealt with improper integrals back in Calculus 1, we had to rewrite this as the limit as n approaches infinity of the integral from 1 to n of our function. And then down here, we have a p-series test. And the p-series states that if we have the sum from n equals 1 to infinity of 1 over n to the p, this is going to be convergent if p is greater than 1 and divergent if p is less than or equal to 1. And we've seen this before in previous sections. So the example says, determine whether the series is convergent or divergent. And part A says the sum from n equals 3 to infinity of n to the negative 0.9999. And so for this, really quick, a little note is that this is not starting at 1. And it's not a big deal if it doesn't start at 1. So it doesn't matter what the starting index is. So it does not have to be 1. So just a little note there. And I can rewrite this as the sum from n equals 3 to infinity of 1 over n to the 0.9999. And using our p-series test, we know that p is equal to 0.9999, which is less than or equal to 1. So therefore, we can say that the sum from n equals 1 to infinity of n to the negative 0.9999 is going to be divergent by the p-series test. So one of the things to note is that if you put down that it diverges or converges, you need to make sure that you're stating which test it is that you have been using. And as we go through these sections, there's going to be a lot more tests that we'll be introducing that are possible to be using on certain types of series. Part B is written differently. Part A was written in summation notation, whereas Part B is listed as the sum of the sequence. And so we have 1 plus 1 over 2 rad 2 plus 1 over 3 rad 3 plus 1 over 4 rad 4 plus 1 over 5 rad 5 and so on. And so if you think about this, that first term, they all look very similar layout. If I were to rewrite that first term and say 1 plus 1 over rad 1 times 1, we can rewrite this as, this would equal the sum from n equals 1 to infinity, since it goes on forever. And this would be 1 over n times the square root of n. And I can also think of this as the sum from n equals 1 to infinity of 1 over n to the 3 over 2. And also using the p-series test, we know that p is equal to, in this problem, 3 over 2, which is greater than 1. And so this means that it is going to be convergent. So this converges by p-series test. And also note that the directions say just to determine whether it converges or diverges. Even if it converges, we do not need to state what it converges to. This test is used not to find that answer, it's just to determine if it's going to be convergent or divergent. So part C is 1/5 plus 1/8 plus 1/11 plus 1/14 plus 1/17 plus, and then on and on and on. And so I notice that the numerator is continuously ones, whereas the denominator is changing. And it looks like I am adding, if I add 3, I can go to term to term to term. And so to write this as a sum, I'm going to go from n equals 1 to infinity of 1 over, and I need to express that as a function. And right now I only have going from 5 to 8 to 11 to 14 to 17 and adding 3 to get to the next term. And if you notice, because we're adding a constant value, that means that it is arithmetic. And again, I'm only looking at the denominator right now. We already decided that the numerator is consistently a 1. And so our formula dealing with arithmetic sequences was going to be a sub n equals a1 plus n minus 1 times d. And so a1 in this case, because I'm just looking at the denominator, is going to be just the 5. And our common difference, our d, would be that 3. So a sub n is equal to 5 plus n minus 1 times 3. And so distributing the 3 and combining your like terms, you're going to end up with 3n, and then 5 minus 3 would be plus 2. And so this would be the formula that would go into the denominator here. And again, you can always check this. So if you were to substitute in 1, you would have 3 times 1 plus 2, and that would be 5 in the denominator. If you substitute in 2, you have 3 times 2 plus 2, which is 6, plus 2, which is 8. And you can keep checking that to make yourself feel better about that. So right now I have this written. This does not follow the p-series test like the other two did, because it's not written as 1 over n to the p. So I'm going to consider using that integral test, but I cannot jump in and use that right away. I have to first show that the function is going to be continuous, positive, and decreasing. So first thing is 1 over 3 to the n plus 2 is going to be continuous. And again, we're only looking at the values that are going to be greater than or equal to 1 for n. And so those are the only values that we're looking at. The only issues that we have would be when the denominator would be a negative value, and we're not dealing with those. Second thing is going to be that it is positive, and if you notice, all of our terms are positive. And our third thing is going to be that it is decreasing. And so first off, you can notice that since we have them listed out, because it goes from 1/5 to 1/8 to 1/11 to 1/14 to 1/17. So it's decreasing, it's getting smaller and smaller and smaller. And so this one is easy to tell that it is decreasing. We have the list of numbers there, and you can tell that 1/5 to 1/8 to 1/11 to 1/14 to 1/17 is decreasing. Those values are getting smaller as we go. And if you were unable to tell, you could also use that first derivative test and show that it is decreasing. And so since all three of these conditions are met, that means that we can use the integral test. But again, you need to first verify that these three conditions have been met in order to use that integral test. So I'm going to go ahead and draw a line here since I'm low on space. And I'm going to rewrite this as the integral from 1 to infinity of our function, which is 1 over, and I'm going to rewrite it with an x, 3x plus 2 dx. If you wanted to leave it in terms with n, you definitely can. And so again, from Calc 1, we rewrite this first as the limit as, and I'm going to use a t, approaches infinity. And so this is going to go from 1 to t, because you can only evaluate definite integrals when our lower and upper limits are equal to a numerical value, not to infinity or negative infinity. So we have 1 over 3x plus 2 dx. And so from here, we have the limit as t approaches infinity of, and it's going to be 1/3 the natural log of the absolute value of 3x plus 2. And we're evaluating this from x equals 1 to t. And so we're first going to substitute in t. And so we have the limit as t approaches infinity of 1/3 times the ln of 3t plus 2 minus, and then substituting in 1, we're going to have 1/3 ln of 3 times 1 plus 2 is going to be 5. And since we're dealing with the limit as t approaches infinity, that is only on this first term here. And if you think about the natural log function, as that goes off to infinity, this is also, our function's going off to infinity. So this is also going to be going off to infinity. So this diverges. So therefore, the series that we have, which is 1/5 plus 1/8 plus 1/11 plus 1/14 plus 1/17, is going to diverge. And this is by the integral test. And so again, the integral test states that if that improper integral diverges, which in this case it did, we can say that that sum or our series is going to also be divergent. And again, this is stated by the integral test. So we have 2 more examples on the next page, and I'm going to go ahead and circle both of those, and we'll work on those 2 together in class. The next thing that we have says estimating the sum of a series, and this is assuming that the series is convergent. So it needs to be convergent in order to estimate that sum, where the size of the remainder r sub n is equal to s minus s of n, which is equal to a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3, and so on, where s is the sum of the series and s of n is that partial sum of the series. So the remainder r sub n is the error made when s of n is used as an approximation to the total sum. So for example, I'm just going to sketch a random curve here. And I'm going to go ahead and say we'll start at n. And then we have n plus 1, n plus 2, and so on. And so if we were to use an approximating rectangle for this, we would have a sub n plus 1, a sub n plus 2, and so on, continuing this on. And so we have r sub n is equal to a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3, and so on. And this is going to be less than or equal to that integral from n to infinity which is adding up that sum of f of x dx, and again the remainder, r sub n, is the error made when s of n is used to approximate the total sum. So likewise on the top of the next page, if I were to sketch the same graph, and instead of starting at n, I'm going to start at n plus 1. And with the next one at n plus 2. And then so on. We have a sub n plus 1, a sub n plus 2, and so on. And so for this case, r sub n equals a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3 plus dot dot dot, and this one is going to be greater than or equal to the integral from n plus 1 to infinity of f of x dx. So, as stated below, the remainder estimate for the integral test is to suppose that f of k equals a sub k, where f is again continuous, positive, and decreasing, which is how we sketched it up above, for x greater than or equal to n, and the sum of a sub n is convergent if r sub n equals s minus s sub n, and again that r is our remainder, that error, then we know that that remainder is going to be bounded by the integral from n plus 1 to infinity of our function and n to infinity of our function. So the example right below this says find the sum of the series, and it's the sum from n equals 1 to infinity of n e to the negative 2n, correct to 4 decimal places, which means it needs to be correct to 0.0001. And so this means that our remainder, or that error, has to be less than or equal to 0.0001. And so in order to do this, our function here is going to be n over e to the 2n. So our function is n over e to the 2n, or n e to the negative 2n. And this is continuous. Since we're dealing with a polynomial and an exponential, those are both continuous, so dividing them is still going to be continuous. Also, all those terms are going to be positive. From n is 1 to infinity. And you can think about this and write out some of the terms, but this is also going to be decreasing, or you can use the first derivative test. So first thing is that r sub n is going to be less than or equal to the integral from n to infinity of our function. I'm going to rewrite it in x's and say x e to the negative 2x dx. And so in order to integrate this, we first need to rewrite this with the limit. So this is going to be the limit, and I'm going to say from t approaching infinity of n to t of x e to the negative 2x dx. And so I cannot integrate this how it's written, but I notice that I have a polynomial and an exponential, so my mind directly thinks parts. So we're going to let u equal x and dv equal the remaining part of it, which is e to the negative 2x dx. So du is equal to dx, and v is equal to negative 1/2 e to the negative 2x. So using parts to rewrite this, we have the limit as t approaches infinity of, and it's u times v, so we have negative 1/2 x e to the negative 2x minus the integral which again is going from n to t, of v du, which is going to be negative 1/2, and I'm going to go ahead and put that negative 1/2 in front of my integral, so this will be plus 1/2, and I have e to the negative 2x dx. And so luckily we can integrate this, so we still have to continuously write our limit until we evaluate this. So we have negative 1/2 e to the negative 2x plus, and then it's going to be the 1/2 times negative 1/2 e to the negative 2x. And we're going to be evaluating this from x equals n to t. So before I evaluate this, I'm going to simplify it a little bit. So we have the limit as t approaches infinity of, and this is going to be negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x. So I can definitely factor out an e to the negative 2x, and then I'm also going to factor out a negative 1/4. And so doing that, I'm going to have a leftover value of a 2x, and then it's just going to be plus 1. And then I'm going to go ahead and evaluate this from x equals n to t. So the first thing I'm going to substitute in is going to be t. So it goes negative 1/4 e to the negative 2t, 2t plus 1, and then minus, and then substituting in n, we're going to have negative 1/4 e to the negative 2n, and then 2n plus 1. Since the limit is as t approaches infinity, the first term is the only one that has t's involved in it, so I need to figure this out, what the limit as t approaches infinity of this function is. And so in order to do that, I'm going to rewrite it a little bit. So we have the limit as t approaches infinity of, and the numerator is going to be negative 2t plus 1. The denominator has a 4, and I'm going to move e to the negative 2t to the denominator, so it's going to be e to the 2t. And if you were to evaluate the limit and as t approaches infinity, you'll notice that we end up with actually infinity over infinity, which is L'Hopital's rule, or negative infinity over infinity in this case, which is still indeterminate. And so in order to deal with this, I'm going to use L'Hopital's rule. And so the limit as t approaches infinity of, and taking the derivative of the numerator, we get negative 2 over, and then taking the derivative of the denominator, we get 4 times e to the 2t times 2, or 8 e to the 2t. And now taking the limit, the denominator goes off to infinity, so 2 over infinity is going to equal 0. And so that limit that we had right here is going to be 0 plus 1/4 e to the negative 2n, 2n plus 1. And this is going to be equal to 1/4 e to the negative 2n times 2n plus 1. And this is equal to our r value, that difference that we have. And this has to be less than or equal to 0.0001. So in order to do this, this is a difficult inequality to solve. And so we have 1/4 e to the negative 2n times 2n plus 1. Again, has to be less than or equal to that bound, which is 0.0001. And so the inequality is difficult to solve. So it might be easier just to use a guess and check kind of method and try different values of n. Remember, n needs to be a whole number. And so if you were to substitute in different values of n, you would try like substituting in 2, see what happens to your value. Is it less than or equal to 0.0001? And no, it's not. And so we get to the value by guess and check is pretty much what we're doing, of n equals 6. and this is actually going to work, which means that therefore the sum from n equals 1 to 6 of our function, which was n e to the negative 2n, which is equal to, because it wanted to find the sum of the series, and we're going to have to substitute in all these values in. So substituting in 1, we get e to the negative 2, plus substituting in 2, we get 2 e to the negative 4. Substituting 3, we get 3 e to the negative 6, plus 4 e to the negative 8, plus 5 e to the negative 10, plus 6 e to the negative 12. And working this out on a calculator, because it wants to find the sum of the series correct to 4 decimal places, and we have 0.1810.